So, transient electromechanical system performance, lecture 4.6, is about two things, really. So the first aspect of the lecture is just talking about how to simulate the transient response of that electromechanical system that we introduced in lecture 4.4, which was that electromechanical system from the lab, right? Which is the DC motor and is connected to the flywheel, right? We're going to learn how to simulate the response from the state space model that we derived. So that's the first thing that we're going to do. The second thing is that we're going to learn how to estimate specific parameters from that system given step response data, okay? And this is going to be very useful to you very soon, assuming you're in the lab, because in the lab we have those devices, and you guys are going to be measuring step responses, and you're going to be estimating parameters from that. You guys are all like giggling over here. What's
We're out of printer money, so we couldn't print off the notes.
Oh, that sucks. Fortunately, there's actually no fill-ins today, so you can print them out later. So, I mean, I am gonna write on it, but you know, it's almost as good. Dodge some bullets. That's right. So here we go. So it's going to be really useful for the lab. There's only one aspect I'm not going to really deal with in the lab that you guys are going to have to figure out how to do on your own with the data processing, but we'll talk more about that. So let's begin. So this is also a MATLAB lecture. So there's MATLAB code in it, mixed in, and the whole thing is available in an M file on the website too. So you can download all that. You're probably going to want to for your lab write-up, I'm guessing. Or you should just write it yourself from scratch. So defining some parameters is first up because we're going to use them in the simulation. So some of the spec sheet stuff, so KT, KV, the motor constants, max torque, max angular velocity for the in terms of the spec sheet. These are just some unit conversions here. Actually, all this is unit conversion. Then we're going to estimate the flywheel J. That's all that. JF. And then we're going to, so the rotor is given in the spec sheet. Calculate the total J there. This is all calculating B, the damping. So it comes from the motor, it's internal damping, and then the damping of the bearings. And R and L, the resistance and the inductance, are given in the spec sheet for the electrical side. And finally, I just say, oh, well, let's use TF instead of KV in this, because we like using TF. Because they're same, right? Just same. Okay. I'm really hungry today. I should have brought donuts. That's what I should have done. That would have been good. You guys missed out. Well, not all of you missed out on, what is that place called? The yogurt, frozen yogurt place? Limeberry. Limeberry on Friday afternoon. Yeah, this is good times. Oh man, I wish I had some of that right now. That would be clutch. Okay. We went to Limeberry instead of doing measurements in the afternoon.
Oh, in the lab?
No, for the class. There were only like 6 people showed up, so I was like, let's go to Limeberry instead of doing a lecture. So, the state space model, I'm not going to do that for this class because I couldn't afford it. 6 people was like, I could do that. This is too many. The state space model was derived in lecture 4.4. Remember, so we went through the linear graph, and we found the state space model, and it was good times too. Not as good at the line variance good times, but other good times. So first we construct the A, B, C, and D matrices in MATLAB, define them as A, B, C, and D. Why didn't we use capital letters? Well, because I really like using capital B for damping, so I have to choose. I use both the B matrix and the damping coefficient to be capital B in the analytic stuff, and I just sweep that under the rug because you have to define this as capital B in your analytic stuff. And also bearing damping, some people use C, but we use C for like constants, for solving the differential equation. I don't know, there's just too many letters to assign, too many symbols needed. Okay, so we've got this, and this was just our A, B, C, D that we defined a couple lectures ago, so I just copied them over, right? Then what I'm going to do is use MATLAB's SS command, which is this wonderful, wonderful command. So you just hand it A, B, C, and D, and it creates an object in MATLAB, but we're going to assign that object to the variable sys. The object is a state space model object, and it has all kinds of built-in tools to use with this state space model object in MATLAB. So we're going to use just one of those today, but there are so many really fun things you can do with it. And we'll learn more about that in the dynamic systems course next semester mostly, but in this term, I do want you guys to at least be able to take these state space models that we have and simulate them using this built-in functionality to MATLAB. MATLAB has. It's like 2 commands, and you can do simulations. We'll learn how to do more stuff next semester, but these 2 things are pretty easy. So SS, hand to your A, B, C, and D. You got to do it in that order. It's expecting A, B, C, and then D. Then we're going to simulate. So the step input is widely used to characterize the transient response of a system. So we're using it to characterize the transient response of this electromechanical system, right? We're going to put in a step voltage, and we're going to see how the system responds. The transient response of a really almost any dynamic system that you have, if you're interested in how it responds to a change in the input, you're almost always going to use the step input to do that. So very common, and this is exactly what you guys are going to do in the lab. MATLAB's step function conveniently simulates the step response of one of these LTI system models, one of these state space MATLAB model objects. So we define that object as sys, right? So we just hand that to this step function. This function is just called step, and it returns to you the simulated output and a time array that's associated with that simulated output. So you didn't even have to define like a time array. It'll even do that for you. It decided how long to simulate it for. It decided what your initial conditions were, essentially 0. But like it just did all of this for you. You didn't have to do any of that. It's almost cheating, I think, to use it. But I use it all the time. So cheat and cheat well. So step just step of sys. I don't think I need to clarify that. Step of sys. So that's going to give us this output. So the time array, I'm gonna print out. So the outputs we chose, like I don't even remember what it was, like 10 outputs. So I didn't want to put out. It would have been 10 columns to print out, and then also I don't know. It was like over 1,000 time steps that it did. So I'm not going to print that whole array out, obviously, because that's a lot of array. But instead I decided to just print out like 6 rows of the time array, so these are the time values. So it starts off at time equals 0 seconds, and then 0.002 seconds, 0.0005. I don't know if I said the right number of zeros on the two, but you get the idea. These are the time steps, and these are the corresponding values of each output at that time step. So at 0.0002, the first of our outputs has a value of 0.0018. The second of our outputs has this value, etc. Okay? So at each time step, we have a different value. So these are like y1, whatever that is, y2. For some reason, these zeros got funky in the columns here. Are they like that in your notes? No. Yeah, it's just, I don't know. I got to figure this out. But for some reason, some of the weird font stuff that happens. Also, the fonts look way prettier. These weird gaps don't happen in your notes either. I don't know. Illustrator. Sometimes. To the moon, Illustrator, to the moon. Okay, so y, so these are the y, and then like there are more y's. There's like 10 of them, right? So like all those columns. I'm just printing out to show you kind of like what this step function gives you. It gives you the simulated response for each of the outputs. Okay, so if one would like the output for a step input that's a scaled unit step, so k times the unit step, by the principle of superposition for linear systems, one can scale the output by k. So if you scale the input by k, you can scale the output by k for a linear system. We haven't really talked about this yet. We'll talk about this more, probably going to be next semester. But if you multiply an input of a linear system by 5, and you already had the output for that system before you multiplied the input by 5, the output you also know is going to get a multiplicative factor of 5 as well. So for the quick and dirty way, so when you guys in your lab, I don't remember how many volts you're going to be stepping into the system, but it's not 1 volt. It's more than that. So you could just stick whatever that is. If it's 4 volts, you would stick 4 there before step, and it would give you the corresponding response. Okay, so it is also interesting to inspect the power flow. Oh, we plot the outputs in figure 4.8. So let's look at that. This is just freaking beautiful, this figure. Oh, it took me forever to make this so pretty. You are welcome. So first off, the horizontal axis here is time, okay, and it goes from 0 to 0.35 seconds. So like this response happens pretty quickly, right? The whole thing is pretty much in steady state after 0.35 seconds. And you guys are going to see this in the lab. This thing is a beast, this motor. So Ryan Haseman, your lab instructor, and I were messing with this over the weekend, and yeah, this thing is quick. Like I feel like we might have almost pushed it to the point where I was a little worried about the coupler breaking, but yeah, this thing is snappy. This thing changes speeds very quickly. So remember what we're doing is we're going from 0 volts, which is going to have 0 angular velocity of the flywheel, to some non-zero voltage. So we're going to just, in the simulation here, we're going to do 1 volt, just a unit step. But in your lab, you're going to do more than that. So we're going to see what happens to each of these variables. So time is the time response of each of these. Now, each graph has the cross variable on the left-hand y-axis and the through variable axis, the y-axis on the right-hand side, because they're different scales, right? They're different units. So 2 y scales, but so each element, so this is the j variables here, this is the L, these are the L variables there. So I plotted omega j. So omega j does, kind of what we would expect it to do, right? It goes from 0 radians per second to 10-ish radians per second. Okay, so it spins up, right, to some approximately constant speed. The torque also looks, it makes sense because what we're doing early on is we're flowing a lot of current to try to get this flywheel to spin up. In order to start spinning up a flywheel, we have to apply some torque to it, right? But once it's spinning, we don't need to apply any more torque to it. So once it's already at the velocity that we're commanding, it's really doesn't need to exert any torque on the flywheel anymore. So that drops off. So there's this bump here where there's a lot of torque, and then it drops off, and then the flywheel slowly comes to equilibrium there. So first take on this is, hey, this is a second order system. Remember we talked about how this is a second order response. It could have been oscillatory, right? Second order systems can have oscillation associated with them. So it could have been oscillatory. It's not, right? It doesn't oscillate. The omega j here, it just decays to its final value. It doesn't have any of this like sinusoidal looking underdamped decay. So that's a good thing. We're going to keep that in mind soon. We're going to be interested in that. Okay, so the inductor, the voltage drops from a positive value to a negative, slightly negative value for a little while. And the current, or maybe it's 0. It's very close. I think it's slightly negative there for a while. And the current, remember the scale's over here for the current, it goes positive, and then it slowly decays back down to negative. Okay? The damper has the same angular frequency, or same angular velocity as the flywheel, right? So that is going to look the same. But the torque is going to increase as the speed increases, right? That's what dampers do. So the torque is going to increase with the speed. And it doesn't go to 0 because at the end, when we're spun up, when our flywheel is spun up, it's exerting a constant torque in proportion to the speed. But it's pretty small. It's 4 times 10 to the minus 4. So that's not a very large torque. Compared to the torque that was required to get that flywheel up, that torque was like 0.06. So pretty much larger than that. Okay, the resistor has this quick increase because current flows through it for the first little burst there, and then it slowly slows down. Because remember, the current and the torque are coupled together. So the current that rises also generates a voltage across the resistor, and then the current slows down, the voltage also drops down. So now we come to the transducer, the ideal transducer. So this is the one side, this is the two side. So what happens on one side has got to have an opposite on the other side, essentially. And because we just have the TF relationship in between them. So the voltage starts off at 0 and it goes to 1. So at first, we instantaneously apply this voltage source at time 0. But the voltage at the one side of the ideal transducer doesn't really get up to 1 until almost the end. So it's slowly getting up there. And that is because, the speed of the flywheel isn't up there yet, right? The speed of the output and the voltage have to be tied together. And then the current, once again, is going to flow at the beginning, and then it's going to decay off. Notice that the current and the torque look like they're just flipped versions of each other. Sign's just reversed. and then scaled, right? Current and torque have the K, KT, but they also have TF, relating them in a negative side. So, and then the angular velocity, of course, is the same as all these angular velocities. It starts at 0 and it goes up to 10. Finally, we can look at the source, which is always going to be at 1 volt, right? We said unit step is going to go from 0 to 1 volt at time equals 0 and stay at 1 for the rest of time. So 1 volt. The current, so right at the very beginning, it supplies a lot of current. All the current that's going to flow into the windings that's going to create torque comes from this source, right? So it's providing that current initially, and then that current tails off because it doesn't need to provide as much current after that. So these are all the variables. So this is kind of like a feel for what happens when you go from 0 voltage to some non-zero voltage in this system. So it's pretty interesting. Let's go all going on there. It's also interesting to inspect the power flow and energy associated with each element. Since we have simulated both the across and the through variable for each element, we can compute the instantaneous power by simply taking the product of them at each time step. And so that's what we're going to do down here, is we're going to say, oh, just take the product of, so the way that these were arranged was a cross variable, through variable, cross variable, through variable for each element. So we take the product of each value with with each across variable with each through variable. So that's what we're doing in this operation there. And we're saying that's the instantaneous power. So we're going to look at the power flowing in or out of each element. And then we're also going to look at the energy. So cumulatively compute the energy contribution of that power for each element. So if we use this built-in MATLAB function, which is cumulative trapezoidal integration. You guys remember trapezoidal integration from calculus? That's what it's doing for you. It will give you the integral, the cumulative, the definite integral accumulating over time. And we definitely always just keep a straight face. And so the product of the two, the cross and the through variables, is the power, and the energy that's accumulating is going to be the cumulative integral of that power, right? So it's kind of interesting to look at this. And this is before we look at the graphs. We're going to try to interpret what, think about how we're going to interpret it. So for energy storage elements, the energy that we're going to be computing is a change in energy from the initial energy stored or supplied by that element. Okay, so energy storage is how much energy is in it at any moment relative to how much it started. Which all of these are going to start at 0 for this case. For energy dissipative elements, it's the change in energy dissipated. So we are dissipating an amount of energy with the energy dissipative elements, and so that's going to accumulate over time. And then finally, for sources, it's the energy supplied or absorbed. A source can technically absorb energy as well as supply energy. So when we look at that, we have to keep that in mind. And for a transducer element, an ideal transducer element, we are thinking about how much energy is flowing through it, right? Okay. So let's look at the resulting graphs, which are also pretty badass. So we've got the power on the left axis. Once again, it's over time, right? Time from 0 to 0.35 seconds. So the power that's flowing into the flywheel, well, the moment of inertia that includes the flywheel and the rotor, it has this peak that happens earlier. Remember, it's the product of angular velocity and the torque. So at the very beginning has zero angular velocity, so no power flowing in. But then as soon as it starts to pick up some angular velocity, and it's got torque applied to it, it's going to have this positive power flowing in. Then when the torque's going to dissipate off, or not dissipate off, the torque's going to decrease, remember, over time once it gets closer to its final velocity. So it starts to slow down, and that's what brings the power back down to zero. But this is essentially charging up the flywheel, right? It's charging up the inertia. And that's this energy that happens here. So this is 2 times 10 to the negative 2 joules that accumulate in the flywheel, in the inertia. The inductor does something interesting. So at the end, the flywheel is spinning, so it has all of its energy that it got, So that's the steady state. But for the inductor, it gets charged up, right, at the beginning. So the power flows in, this thing gets charged up, but then it actually returns its power to the circuit. So notice that the power flows in for a short period, and then it actually is very slightly negative for quite a while, and so it's actually flowing that power back out, that energy back out into the circuit. So the inductor doesn't stay energized in steady state. And that's because in steady state, remember, the voltage across the inductor is 0. And so the product of 0 and anything is 0, so the power's got to be 0. Okay, the power, now this is a dissipative element, right, the damper. So the damper is going to have some power that's going to flow into it, positive, it's going to flow in, and that power is going to approach some constant value. So and that's when the damper / flywheel speed is at some constant value. It's going to be dissipating energy at some constant rate. And so that energy is just going to keep increasing. So we're dissipating energy that's just accumulating. And it's going into thermal energy. And hopefully you're getting that heat energy that you're dissipating from the circuit, or from the mechanical side actually. Hopefully you're getting that out somehow. Otherwise you're going to heat up, right? We don't want to heat up too much. And this is where that heating comes from on the mechanical side. On the electrical side, the heating comes from this other dissipative element, the resistor. So early on, it has some current flowing through it, and that creates this power flow in. And that pretty much goes to 0. The current is going to be very, very low in steady state, so we've got this pretty much leveling off the power that's or the energy that's dissipated by the resistor. So notice that so if you spin up your flywheel, it's really only dissipating energy. It's really only heating up due to the damper in steady state, right? Because the damper, notice, energy that's being dissipated still keeps rising, right? There's still some non-zero power flowing out of the damper because it depends on the speed of the flywheel. But the current's done, so your resistive heating goes to 0, and it's actually not a big deal. So most of the time in steady state, we don't worry about heating that much. As long as that steady state is not one that requires the current to be significant. So if you hold on to the flywheel, don't let it turn, and you put in some non-zero voltage, it's going to want to turn, and the current, it will flow a lot of current, a lot of torque, a lot of current will happen, and it will heat up significantly. But when the flywheel is free to rotate, it should be fine. So then this is the transducer. So what happens with the power of the transducer is exactly the opposite, because everything that flows in side 1, power flows in side 1, it flows out side 2, right? Positive in, negative out. So it flows in and then it flows out of the other side. So the energy that went through it is 2 joules, and so the energy that came in is 2 joules, and 2 joules left. That's a good sign. We were hoping that that would happen. If that didn't happen, we screwed up somewhere. And then the source, of course, is supplying power early, not as much power when it's in steady state. So that's why we looked at all the variables in our output, is that we wanted to see all these things. We're kind of interested to see. So now, you guys are going to go in the lab and you're going to be like, okay, I remember that the power is being dissipated. The dissipation power early is quite a bit because of the resistive element, but then it's going to go to 0 when it's in steady state, whereas the damper one is going to increase steadily, etc. So hopefully you guys have a feel for it now. All right, so that was that. I also printed out some values from those arrays just to give you a feel of what the MATLAB arrays looked like before I plotted them. But clearly, the graphs are the one that we can actually get a feel for it. Can't really get a feel for it looking at the arrays. So, so this is the second part of the lecture. So the first part was like, okay, here's the transient response. Here's how to simulate the transient response. Here's what it looks like, and here's how we can get a feel for it. Now we're going to talk about how to estimate parameters from the step response, which is specifically geared towards how you're going to estimate a parameter, actually 2 parameters, in the lab from the data that you get. So often our model has a couple parameters we don't know well from the specs, but must attempt to measure. For the system under consideration, perhaps the 2 parameters most interesting to measure are the dominant time constant, which we're going to call tau1, time constant, and the transformer ratio, TF. In this section, we explore how one might estimate from a measured step response these 2 values. Other parameters in the system could be similarly estimated, and there are some pitfalls there. You can actually estimate the damping this way too, and I was originally going to have you guys do that, but then I actually did this analysis, and I discovered that the sensitivity to parameters changing for the damping estimate is really bad. So your uncertainty would be horrible. So I didn't want to make you guys estimate a parameter with a huge uncertainty associated with it. Probably the spec sheet's value is better. So what it means is not that you can't know that value. It just means that this isn't a great way to estimate it if your measurement is very sensitive to changes in that parameter. So this is. These 2 are good things to measure from the step response. The dominant time constant and the transformer ratio. Those are both good to estimate. So we're gonna estimate those 2 in the lab too. So this is I'm gonna pretend to be doing the lab here by spoofing some data. It's gonna be fun. So let's do a little bit of discussion of the analytics first. So by way of the transfer function, which you guys don't know what that means yet, the state space model can be transformed into input-output differential equations. So next semester you guys will learn more about this. But essentially there's another representation of the system. That's not a state space model. It's not a linear graph model. It's not a input-output differential equation model. It's a transfer function model. But it's really useful to use to bridge in between the state space model and the input-output differential equation model. And then you don't need to understand this part. I'm using symbolics to do this. But the differential equation for omega j is just this. So we just use the transfer function as a bridge to go from state space to our input-output differential equation. And we'll learn how to use that bridge. It's pretty easy to use, but you just don't understand the concepts that need to go into it yet. You will soon. So when you guys do your analysis for your labs, you can just use this equation of 4.12. This is a second order, so it's a second order system. So any differential equation you're going to write from the state space model is going to be second order. So it's second order. Omega j is the output of this differential equation. Vs is the input. So when you solve this differential equation, you're going to get out omega j as your solution. So following the usual path, the corresponding characteristic equation is this. You solve for lambda, which are your characteristic roots. You get this. Annoyingly, all of my brackets are just strange looking. But they're not in the notes as usual. So for a step input of magnitude k, so k times the unit step, and 0 initial conditions, and distinct roots lambda 1, lambda 2, the solution is this. So where this is missing parentheses too. So this is your solution. Let's compute lambda 1 and lambda 2 for our parameters. They come out to be these. Both values are real. They both come out to be real. That's nice because it's a little easier to work with, right? If they were complex, we would be expecting there would be oscillation. So we'd have that underdamped case. But in this case, we have real roots, so expect no oscillation. And we're just going to have these two exponentials decaying to 0 in their response. However, that decay occurs with two different time constants, right? It's not just like the first order case, you just have one time constant. The second order case, when you have these two real roots, you have two different time constants for your decay. One time constant is negative 1 over lambda 1. The other time constant is negative 1 over lambda 2. So we computed what tau 1 and tau 2 are, 0.0612 and 0.0027. And I took the ratio in between them because I was curious to see how different are they. So tau 1 is 23 times larger than tau 2, which means that tau 2's exponential is going to decay really quickly compared to tau 1. And the slower time constant is going to be dominant, so tau 1 is our dominant time constant. Because tau 2 is over so quickly, right? So that decay happens so quickly that tau 2 is the one that dominates. Most of the response is just tau 2's response. Or sorry, tau 1's response. So, the second decay is much faster than the first. That's good news for our estimation project because we can easily ignore the step response's first 5 tau 2, which is the fast one. And assume the rest is decaying at tau 1, which we call the dominant time constant, which we would like to estimate. So if we come back over to the graph of j, we don't see this very well, but you can kind of tell that it doesn't immediately enter this nice decaying exponential. What it first does is it has a little inflection that happens. It's kind of exaggerated a little bit for effect. But it has this inflection, and that's when your tau 2 is operating. Your tau 1's operating after that, almost exclusively. So when we get this response data, what we're going to do is we're just going to lop off what happens back here. We're just going to say, ignore that, because tau 2 is still operating in that regime, so there's both decays happening at once. We don't want to ignore that. And in fact, you can see approximately tau 2 operating in the torque. So the torque, this is approximately how fast it takes tau 2's response to be finished. And then tau 1 takes over after that. So we're essentially just going to cut off this part and ignore this part of the data. Okay. Good. that is that. Okay, lost my spot. There we go. So let's generate some fake response data to get the idea. We'll layer on some Gaussian noise with rand_n to be more realistic. So what I do is I just take our analytic expression for what the solution is. So this is just equation 4.15. And then I evaluate that at a bunch of different time steps. I simulate this thing out. I say, okay, generate time steps from 0 to 6 tau 1. Or, yeah, take 6 tau 1, so the dominant time constant. So 6 of the long time constants, which should be like 99.98% decayed by then. And give me 200 points in between there. So then I evaluate our analytic solution, but I don't want to get data. I don't want to spoof data that looks perfect, because that doesn't look like data. And you're not going to run into some of the issues you're going to run into if you just take that clean data. So I add in a Gaussian random variable distribution here, with 0.5 standard deviation, which gives me this data. Okay, so we made up, this is just, I mean, this is like what you guys might get when you measure your data. Except for what you guys are going to do is do multiple of these responses, not just one. So you guys are going to have, the one thing I'm not going to show you guys how to do, and this is, not that I'm keeping it a secret, I just didn't have time. But you're going to have to just put or average these responses. So you're going to have to take this long response data, which looks like this, etc. And you're going to have to say, oh, I want to take this chunk here, and I want to put it on top of this chunk here, which is supposed to be the same response. And I want to average those two so that you're going to get tighter groupings here. So anyways, that's the one difference you guys are going to have to use. But so this is noisy. And we want to estimate tau 1 and TF from it. So let's trim the data to, so the first thing is to eliminate that time interval corresponding to the first 5 of the fast time constant tau 2. So we're going to say tau 2 is operating in some region at the beginning, and we're going to just lop that data off. We're going to go 5 time constants of the fast time constant out, which is like 99% of the effect is gone in that region, and we're just going to cut it off. So we do that. This is just a little trick to, not really a trick, but this just computes the data point that's closest to 5 tau 2. And it gives me the index of that data point so that I can say, okay, ignore the rest of that and just take the stuff afterwards. And that's what I do. I called it I5 is the data point on the boundary. So I take the next one and I go all the way to the end of T data. And so that gives us truncated data. So we want to take the natural logarithm of the data so we can perform a linear regression to estimate the experimental slow time constant, tau 1 tilde. So the rest of this data is essentially e to the minus t over tau 1, right? So if we take the natural log of it, we're good. But there's a problem. Well, there's a couple issues we have to deal with. First of all, this is actually not just e to the minus it's something minus something e to the minus t over tau 1. Because we're decaying not to 0, but we're decaying to some constant value, right? Whatever the steady state speed is. And so we can't just take the log of that. If we take the log of that, that is not going to give us a linear function in tau 1, right? You guys may or may not have run into this when you guys were doing your thermal response data. I saw it a couple of times. So what you want to do is you want to essentially subtract off this value before you take the log. And that value is the steady state value. Actually, you want to subtract off this from the steady state value, which gives you the right sign. But essentially, that's the idea. You got to find out what this value is so you can subtract that off, okay? And that is our steady state value, omega j infinity, which we're going to need anyways to find TF. So we want to find tau 1, we want to find TF. So omega j infinity is actually the key to both of those. So we don't want to just take the last value in the array due to its noisiness. So if we were just like, oh, well, the best one's going to be, for the steady state, it's just going to be the last value. But it's noisy, so this is actually a really shitty value for the final value. Crappy value for the final value. So this is not a good estimate of the final value. But you can't just like take the mean of this whole thing, because the mean of this whole thing is going to be like there. That's not good either. So what we're going to do is we're going to take the last, so this last little interval here, and we're going to average that. And we're going to say that's probably the best estimate for our final value. So what we choose is the last time constant of the slow time constant. An interval is the length of the slow time constant, the very last bit of it. We're going to average that, because it should be 99% there for that last interval anyways. So that's what we do. We use a similar routine here to essentially just take the average over that last little bit, and we get 10.18 as our average value. So our average is like here for this last little chunk, which gives us the steady state value approximately, a good estimate of it. And if we were talking about uncertainty, which I didn't go into an uncertainty analysis, but if we were interested in an uncertainty, we would be interested in the standard deviation of the means associated with that. So I computed that in case you needed that for your write-up. I don't know. Okay, so let us use this result to transform the data into its linear form. So we do that. We take the log of, and we take this difference. So we think we're good, except, oh no, what happened? 33 of these, when we did this transformation, ended up coming out complex. And that's because we took the log of a negative number. Essentially, we transformed this thing to look like a decaying exponential, which is great. So now we can take the log of it. But since it's random, some of these values wander off into negative land. Negative values come out complex if you take the log of them. And you can't simply just take the real part. That would actually be worse than just getting rid of the point. So there are some ways to deal with this. So a naive way to deal with it would be to just take the real part. Where did I do this? Yeah. So logarithms of negative numbers are complex. Naive approaches will just are just like taking real parts or excluding complex values or coercing complex values to negative infinity. All have issues of biasing the data. So these values are coming from like these ones right here that are wandering up above the steady state value. That's where our issue is. But if we just simply lop off all those, we're going to bias the data in a certain direction, right? Also, we can't just take the real part. Essentially, we're going to be biasing it any way we cut it in that way. So there are some options that we have. So the first option, probably the best one is to do a nonlinear regression, but that's beyond the scope of this course. Also, a pretty good option is doing discrete filtering, which is also more of an advanced signal processing technique. Good technique, but we just don't have time to do it. MATLAB has a nice function, filt, you could use to do that, but it essentially just smooths it out. It's really nice. But we're not going to be able to do that in this course, so instead, we opt for an easier approach. We find the index at which the time series first transgresses the boundary, so first goes off into negative land, and exclude the data beyond the previous index. So that's what we do. We find the first complex one, and then we say, oh, okay, we're just going to truncate again, and we're going to just get rid of all the data above that. Which isn't like the best solution always, but it's better than some of the other solutions we could have chosen. This is like the least bad solution, which is how a lot of people defend capitalism. So this is plotted in figure 4.11. So here it is with the data. And the reason that the spread gets larger and larger is that we have a logarithm that's being taken here. And notice that this is pretty linear, the average of it is. So we can do a linear fit to the data, which is really easy in MATLAB. Just use polyfit, and you can find what the time constant is then as the slope of that. Well, actually, negative 1 over the slope of that. 0.063, so 60.3 milliseconds. Recall that our analytic expression for tau1 is known in terms of other parameters. Similarly, the steady state value of omega j, which has already been estimated to be 10.18. Oh yeah, this is not a complete sentence because this is not supposed to be there. So omega j, the steady state value of omega j has already been estimated to be 10.18. This occurs when the time derivative of omega j, the time derivatives are 0. From the solution for omega j, or its differential equation, realizing that when this occurs when the time derivatives are 0, for constant voltage input, this occurs when this equation is true. So this is the steady state value analytically, according to our model. So we can solve this for TF, which is this, okay? So we can choose the solution closer. There's two solutions, right? Plus or minus. We choose the one that's closer to the a priori or spec value of 0.0974. We evaluate it and it come out to be 0.0976, which is very close to 0.0974 because we constructed it to be so, right? I mean, we constructed this data from a model that had TF equals 0.0974. We estimated it to be 0.0976. But that makes sense in this case, but it's because we spoofed the data, right? Real measurements would probably yield an estimate further from the spec, which is why we would estimate it, right? If we trusted the spec, then we wouldn't really need to estimate it. But we're saying, okay, TF for this motor, let's figure out what it is. So dominant time constant, tau1, we measured that. We also measured the transformer ratio. Well, you guys are going to. I just made up data. You guys are actually going to take data. So, all right. That went a little long. My bad. Have a good lunch.